Let's spend a minute or two exploring the Lorentz factor, which is often given the symbol gamma, Greek letter gamma. So just remember it's 1 over the square root of 1 minus v squared over c squared. Came out of our light clock analysis as the key factor in the time dilation equation in terms of moving clocks running more slowly. But the question arises, of course, is why don't we see this in everyday life? And the reason we don't see it is this v squared over c squared factor. If this is small compared to 1, then this is pretty much 1 over 1, and gamma is about 1, and we don't see any difference. The elapsed time on a moving clock is the same as elapsed time on an identical stationary clock in terms of how precisely we can measure it. So what we've done here is just list some speeds, and then the results for gamma for each of those speeds. And it's a useful and or fun exercise for you just to plug in some numbers here, do the calculations, and come out with your own values of gamma. But here they are. So speed 0, we've done this before, then v is 0, so this just 1. 1 divided by 1 is gamma is 1. So no effect if the two clocks are actually right next to each other. If we have a speed of 0.5 kilometers per second, which is 1,800 kilometers per hour, and if you think in terms of miles per hour, it's about 1,000 miles per hour, and roughly the speed, say, of a supersonic jet. Okay, so that's pretty fast in our ordinary experience. If you see a supersonic jet going by at that speed, the speed of sound is about 700 miles an hour, depending on atmospheric pressure and a few things like that, and therefore you'd definitely be getting a sonic boom out of this. But look at what the gamma factor is. Okay, exactly how many zeros we got there, but it's way out here, and I think this is probably about 100 billionths right here and on. So even at supersonic speeds, very, very small difference between in terms of the clocks being measured, moving clock versus a clock on the ground, as it were, a stationary clock. Although I should say that they've actually done experimental tests where they've had two identically prepared atomic clocks, so very accurate clocks, and they kept one on the ground. They put one up in an airplane, essentially a jet. I don't think it was a supersonic jet, but just a large jet. So it was flying at certainly several hundred miles per hour, kilometers per hour, 600, probably in that range, 600, 700 miles per hour, maybe 1,000 or so kilometers per hour. And they were able to see a difference, actually, when they brought the clock that was traveling back down again, the clock that had moved, and compared it to the original clock. Now, they also had to take into account a whole bunch of other things in that experiment, including gravitational effects and the general theory of relativity. But using the results from the special theory of relativity, they were built into that experiment as well, and it was confirmed there. Some other speeds here. Now we're going to switch to 0.001 c. Okay, so tens, hundreds, thousands. This is 1/1000th the speed of light, about 300 kilometers per second, or in terms of miles per hour, it's about 190 miles per hour, something like that. I think around 200 miles per hour, not quite 200 miles per hour. So obviously, very fast. I'm sorry, not miles per hour, miles per second here. Okay, 300 kilometers per second. About 190 miles per second. Okay, so we're not talking about a fast race car here. We're talking about something, getting into, say, rocket ranges and things like that with this, or even rockets, aren't going 200 miles per second typically. Maybe get up there. And look at the gamma factor. Okay, again, tens, hundreds, thousands, 10,000s, 100,000s. Millionths, it looks like it's in the 10 millionths place there in terms of the effect. So again, very, very small effect. And then as we increase the speed, you can see what happens. So now we go up to 1/10 the speed of light, 30,000 kilometers per second. Okay, 30,000 kilometers per second. This is probably a little less than the circumference of the Earth at the equator. I know it in miles. It's 24,000 miles approximately. So it's going to be a little more than this, but roughly once around the world, give or take a little bit. And that speed in 1 second, and gamma factor 1.005. And then as it goes up half the speed of light, now we're sort of getting someplace where we could see some effects, certainly. Not that you couldn't see it before, but they're pretty small. 1.2 there, 9/10 the speed of light. An object moving at 9/10 the speed of light, 270,000 kilometers per second, roughly. 2.3 for the gamma. Then 0.99 c, 99% of the speed of light, 7.1. And then 0.9999 c, 4 nines there, 71. So it does go up fairly rapidly as you get to speeds very close to the speed of light. And of course, if, as we mentioned, if you have v equal to the speed of light, you get infinity there, which would then therefore imply it's some sort of an absolute limit. You can't quite ever get there. Okay, so that just gives us a sense of when we're talking about relativistic effects, at least for special relativity, most of the time we're going to be dealing with things, if we're actually going to see any effects, with speeds at about half the speed of light or greater. So somewhere half the speed of light up to 0.9 c, maybe a little higher than that. Whether we can get those speeds, that's another matter. We can certainly generate speeds like that and even higher in particle accelerators, and that's where you really see relativistic effects. In fact, to design current-day particle accelerators, you have to take the special theory of relativity into account to get them to work right. So this is a very practical matter for the engineers and scientists who are working on those matters. So just a little bit exploring the gamma factor, the Lorentz factor, gamma, give you an idea of when it actually becomes a larger factor in terms of the speeds involved.